Hello. Welcome back to Chem 161. This is the last lecture of week 9, and there's not much left after this. After today, there is an exam on Monday, a short lecture on Tuesday to finish off whatever else we need, just a Q&A on Wednesday, which nobody will probably come to. And on Thursday, there is no class because it's just the final. I'm going to post the final, you do the final, I grade everything, then we're done here. So, we're getting pretty close to the end, which is good, but that does mean that now that we're coming down to the wire, you got to make sure that you are prepared for all of the material that I'm going to cover on exam number 2 and the final. Exam number 2 is cumulative up past exam 1, so everything past like the Rydberg equation is fair game. So most of chapter 3 and then all of chapter 4 that we cover up through today. The final exam is cumulative completely. It will be the entire class, and it'll be very similar to the midterm exam 2, with one little last thing that I'm going to put in there, and then not mention that until Wednesday, where there will be an announcement about it. So make sure you know the material. I know that people are passing around quiz questions and taking pictures of the quiz, and like that's fine. I don't care. That's the kind of the point of the quiz, is like this is a low stakes assessment. There's going to be things in place to prevent you from doing that more or less on the exams, as you know, because like their questions are one at a time, and that slows you down. So, and then the final exam will have another further implementation along those lines. And it is definitely in your best interest to make sure that you know the material in order to be successful. I'm still not going to restrict you from relying on other people if you absolutely have to, but you will time out if you do that on the final. Like, you only get 2 hours to answer 150 points worth of questions, and you got to move fast. We're going to channel our inner Sonic the Hedgehogs here, and you got to go fast. All right, where are we? Here's where we were. I gave you these 5 basic shapes yesterday: linear, trigonal planar, tetrahedral, trigonal bipyramidal, and octahedral. The names are on the previous slide here. There we go. And I also gave you the PHET link. Can I copy and paste that in here again for you? Let's do that. Just in case you didn't see this yesterday, here is the link to play around with that if you'd like. I just think that that is such a useful resource that I just want everybody to have it. All right. And so what we're going to do today is, now that we have learned how to classify molecules into one of these electron pair geometry categories, we are then going to further subcategorize molecules based on their molecular shape, using the assumption that electron pairs, while they exhibit a force because they have a charge, electrons are very, very small relative to the size of atoms. So any electron pairs that are non-bonding are essentially going to occupy what we'll call blank spaces. Those spaces will just, they'll exert their force and keep the shape the same, but they won't, say, have a little lobe here. So, like, for instance, if I could click on the right thing, that'd be great. There we go. For instance, with this right here, this 3-lobed shape for trigonal planar, if I had, let's say, here's my atom X in the middle, and then I had A on the sides here, I would make a triangular shaped thing. But if one of these was an electron pair instead, because electrons are so small, the effect is that you don't even see anything here. The shape remains the same, and you would end up with a molecule that has this shape. And there's just this mysterious void over here. But we're going to draw in the electrons just so that we know. This isn't trigonal planar. When you look at it like this doesn't look like a triangle at all. It looks kind of like a bent line. So we're going to give it a different name. And so that's where molecular shape comes in. We're going to turn electron groups or domains into electron pairs, and then just omit them from the overall shape, but keep their presence that affects how the shape came to be in the first place. All right. So again, the molecular structure of a molecule uses the base template for whatever molecule we're looking at. So if we were looking at something with 5 electron domains, it'd be trigonal bipyramidal. And then we start omitting electron domains for any non-bonding electron pairs that are present. For those, we just don't put an atom there. We just put 2 dots, and the shape remains in that configuration, but there's no atom there. And so the overall structure of all the connectivity of the bonds ends up looking different. Okay? So we omit electron domains for non-bonded electrons. As a result, the shape is going to be slightly different. And we end up creating a chart on this page that shows that. We're actually going to make this chart over here. I didn't zoom in before I started this today, so there we go. All right, so what we're going to do first, I'm just going to hide this up at the top because we don't really need it. What I'm going to do is we're going to say number of electron groups and then we'll say the Vesper geometry. You know what? I should actually use the terminology that your textbook... Oh, darn it. Hold on. Everything is terrible. I didn't tell it to draw on another layer. And it doesn't do it by default because, of course, it doesn't. Okay, there we go. That should be fixed now. All right, so now we will do... So number of electron groups. And then we'll say electron... Oh, I don't know what the geometry... I always call it Vesper geometry. So electron pair geometry, I think it is. So we got 2, 3, 4, 5, 6. All right. So this geometry that we're going to do in black here is going to be exactly the same as we had yesterday. So you should know all of these names by now. We got linear. We got trigonal planar. We've got tetrahedral. It's not a very good tetrahedral. That's okay. We have trigonal bipyramidal. And then finally, we have octahedral. All right, so the next thing that we're going to do is that we are going to draw... Or not draw, we're going to write a new column. So, number of non-bonding electron pairs. And then the resulting molecular shape that arises from that. Now, this is going to be kind of like if I were to take the table and go straight across. I'm going to run out of space here, probably. But I'm going to try and fit it in the best that I can. we're going to start with a number of electron groups and then start replacing the electron groups with electron pairs. Now, the first one is always going to be a copy-paste of the default shape. So if I do this, this would be 4 if none of them were non-bonding pairs, because I just copied the shape and pasted it. If one of them was a non-bonding pair, then that would look like this. Here's my shape. And then I erased one of the positions and replaced it with electrons. Boop. Now, if you end up with 2 atoms in your structure, the result is always linear. Because there's no way that you can have 2 atoms along a bond that isn't linear. Bonds don't turn corners, they don't arc, they don't curve. They're just straight lines. So anytime we get down to 2 atoms, we're kind of just uninterested in the shape anymore. So for the linear electron pair geometry, the only possible outcomes are all linear. So if you see 2 things around a central atom, whether they're electrons or atoms, it's linear. And that's not super exciting. But when we get down here to trigonal planar, this will make a lot more sense. And can I get all this in here without... Yeah, that'll work. The selected area is empty. Oh, great. Are we making new layers? Yeah, that's just what I wanted. Hold on. Merge down. Merge down. Of course, there's no hotkey for that. Okay, so now that should work. All right. So for 3, if I have no electron pairs for 3 electron groups, then the shape that I'm going to get is just the default shape, which is this one. But let's suppose that I removed one of them and turned it into an electron pair. That would be like doing this. Whoop, goodbye. And so now the shape that I've made is no longer a trigonal planar. It's more just like a line that has been bent to a certain angle. And so we actually just call it that. We call this bent. You might also see the term angular. But really, it's bent. All right. I have to actually neaten this up because I've already messed up my table. So give me just a second to do that. What do I want to do here? I want image, canvas size, and I want it to be twice as tall. That's almost sort of what I wanted. Oh, that's not what I wanted. Sorry, just a second. This'll work, I just need a moment. Oh, that's not what I wanted. Hold on. All right, so now I gotta do that. All right, hopefully this will be enough space for me to work with here. I should have budgeted this out a little bit better. Oh, darn it. Don't worry, everybody. I got this. There we go. Okay, that looks a lot better. Oh, I hit the thing on my mouse. Sweet. Okay, so now we're back in business. All right, so that's what we have for 3 here. So for 3, we only have 2 options. There's either no electron groups and the shape remains the original trigonal planar, or we have 1 electron group and then the shape becomes bent. Yeah, I know. That's the trick to doing this on the computers. I could just pick stuff up and put it wherever I want to. In fact, this is kind of... There we go. That's a lot better. All right, let's do 4, because 4 has some interesting things here. So first we got to copy this guy, because this is going to be 0. And then we want to look at 1 and 2. So I just want this shape here. Apparently I didn't get all of it, but that's okay, because we're going to erase that one anyway. So I'm going to erase 1 of the electron groups. That's actually not a good one to do, now that I think about it. Let's do this one. We're going to turn that into an electron pair. And you'll notice that this looks kind of like the shape that we just had, but now it's a little more squat and short. And so because it looks kind of like a pyramid with a triangular base, which I'm trying to like shade in right here. So the faint purple that I'm adding is like the base of this little pyramid that I've got. The term that we use for this is trigonal pyramidal. Or trigonal pyramidal if you don't know how to pronounce the word pyramidal. That works too. So that's the first one. And then the second one that we have, we'll just take this guy and put him down here. We're going to erase the same one that we erased before, but then we're going to erase the second one. If I could find the eraser. There it is. So here's the first one. We're going to get rid of that. And I'm going to get rid of this one too. And we'll put electrons in both of those positions. And now what we have is another bent line. It's not linear. It's bent. You can call it angular, but don't call it angular. Call it bent. All right, so those are the molecular shapes for 4 electron domains. All right, next we're going to do 5. I have to merge layers again. As far as I'm aware, there isn't a hotkey for that, unless I set up a macro. All right, so for 5... we have some really interesting considerations in 3D, because the shape for 5 is actually very unusual. All right. Oh, I didn't copy the text with it this time, just to... That's probably silly of me. We'll just do that. So if none of them are electron groups, the shape is retained. But if one of them is an electron group, we have an interesting issue that we have to consider here. And that is, which one do we take? Are they all the same? This is the first shape where it's kind of like, there's kind of a weirdness with symmetry here. And to do that, we actually have to start considering bond angles, which I need a different color for. Let's do... We'll make this very cyberpunk today. We'll do kind of pinkish purple and blue. So here we go. if I were to look at the bond angle that I've drawn here, which I can't see because this is in the way. There we go. What number would you assign to this blue arc right here that I've labeled with a curve and a line? Based on how I've drawn it anyway. And it is 90 degrees, that's right. So the angle of my vertical line and my horizontal line will be 90 degrees. And all of the ones around that will also be 90 degrees as well. Because it's 3 atoms in a triangular plane and then an extra one coming out at the top and the bottom. But with that said, let me get a different blue here. Let's get a darker one here. What's the angle right here between 2 members on that equatorial sort of plane? Well, it's a triangle, so what angle could that be? That one's 120 degrees. Interesting, okay. Now, what did we talk about at the very start when we were mentioning geometry? What do electrons want to do when they repel? Do they want to repel a little bit or repel as much as possible? Or are they just like, whatever? Yeah, electrons repel like crazy, right? So if I had to remove one of these and turn it into an electron pair, I want to remove the one that gives my 2 electrons as much space as possible. The reason being is because I'm turning electrons that go along a bond into 2 electrons that are just kind of hanging out. And if I have 2 electrons that are hanging out, I need to give them as much space away from the other bonded electrons as possible. So which one is further apart? These 2 that are 90 or these that are 120? So the one on the right side is one of the ones in the center, and it's 120 degrees apart from its neighbor and 90 degrees apart from the top and the bottom. The one on the top is only 90 degrees away from anything. So it turns out that this one is closer to stuff, and this one is further. By virtue of there just being a 120 degree angle. So what we're going to do is we're going to get rid of the ones that are furthest away first. And because they're further away, that gives us more space to put our electrons in there. So I gotta go back to the black ink here. What that means is that when I erase over here, I could choose either a top or bottom one, or I could choose one around the center. And for the reasons that we just explained, we want to take the ones around the center first. These are called equatorial, because they go around the equator, more or less. The top and bottom ones are called axial, because they kind of go along the axis of rotation. And we're going to remove the equatorial ones first, just because the bond angle is bigger, so there's more space for when I put these electrons in here, for those electrons to be. And hopefully what I just said, yeah, that was what I was hoping. We're going to pick the position that has the biggest bond angle, because that gives us the most space for these electrons. Because these electrons are just going to sit here. And you can see they're kind of close to the atom. And they're going to push everything else away. Now, the shape that we make here looks really stupid, so we're going to give it a stupid name. How about seesaw? That sounds great, right? And the reason that it's called this is because if you rotate it like 90 degrees like this, it looks kind of like a seesaw. Chemists are dumb. Hey, guess who ran out of space again? Oh, don't give me your selected layers empty bullshit. Hold on. There we go. Okay, I should still have this. Uh-oh, what did I do? Undo. I didn't have it copied, so we'll just make another one of the. Oh, goodness. Why is everything the worst? We'll just copy this guy again. All right, so let's do 2. We're going to erase the same that we did before. There it goes. It's gone. And then when we remove a second one, for the same reason, we're going to remove another equatorial one because the equatorial ones are 120 degrees apart. So I'll just pick this one. And we'll put in the electron pairs right where those were. And now this looks kind of like the letter T. We're going to call it T-shaped. And then finally, I could do the same thing one last time. I don't know what I just did there. I moved like the origin of the marker. Ah! Yeah, that's fine. And I'm going to get rid of the first equatorial that we did, the second equatorial that we did. And then we're still going to get rid of equatorial because we're removing equatorials first. So here we go. 1, 2, 3. And wouldn't you look at that? That looks like a very straight line. And it totally is. We're going to call it linear. This linear should not be confused with the linear up here. Even though they do have the same shape, there's no electrons around the linear up at the top for 2 groups because there's only 2 groups. But for 5, you can actually get linear by peeling away all the equatorial stuff. Surprising absolutely nobody. I gotta move this guy again. As neat as it is that I can just copy and paste and drag stuff around. Ooh, that's not what I wanted. Undo. I would much rather do this on the whiteboard. Alright, so select all, select none. Canvas size anchored to here. Okay. And then I gotta paint it white on the backdrop. Oh, and everything is gone. Hold on. I clicked off of it. Which one's bent? I'm sorry. I missed that while I was copying and pasting. So the linear one with the unbonded pairs is actually linear. I don't know why this one didn't show up. Hold on. Because if you go back to the default shape, these were linear from each other, and then I have this going around the center, and I've axed those, so what's left is totally linear. And you can see that linear template that remains as I go through each drawing. I'm not sure why this isn't copying and pasting. Copy, paste. Oh, there we go. It worked this time. All right, so if I don't add any electron pairs in here to replace things, it'll still be octahedral. If I replace one of them, which one do I take in this case? Like, what's the one that you choose here? Well, let's consider bond angles. What's the bond angle right here? It's the wrong color, but that's okay. What is this bond angle here? And then what would this bond angle be? Yeah, aren't they all the same? What are they all? It looks pretty straight lined up to me. Yeah, they're all 90 degrees. 45 would be half of that. So if they're all 90 degrees, I can take whichever one I want. Ain't nobody the boss of me. So I'm going to take this one. Goodbye. And now what I have is, if I paint this really faintly, what I have is it looks kind of like a pyramid with a square base. And so this is called square pyramidal. I ran out of space. Can I? No. There. I'm trying, you guys. I really am. All right, so that's square pyramidal. That was for one. If we had two... Oh, I don't know what that did. I moved something on accident. If I have two, I would get rid of this guy right here. But now which one do I get rid of? Well, if my electron pair that I replace it with is right here. Electron pairs repel bonds, but they also repel stationary electron pairs even more. So I want my electron pairs to be as far apart as possible. So that means that the option that I have to pick to ensure that they are as far away as they can be is actually the one across from it. And then I just have the square that remains, so this is called square planar. So those are the shapes. So you got to know the names of these shapes that create the chart. So that's how we made this chart that you can see right here. And you can see that for 6 shapes, it keeps going to T-shape and linear. We've already seen those shapes, and you could probably make the assumption that, oh, okay, if I just get rid of this thing, then it will look like a T, and if I get rid of the next one, it'll look linear. So I'm going to skip those. And in fact, you don't really ever see these combinations down here. So these guys that I'm highlighting in yellow are exceptionally rare. Also listed on here are a bunch of bond angles. The bond angles are helpful for letting us determine geometry by just looking at what the angle is. We can also make some predictions about bond angles. It's worth knowing what the angles are. Just so you can say, oh, those are all 90 degrees, and then you can remember, okay, I have to take this electron pair first on, say, trigonal bipyramidal. If you go to that link that I linked you at the start here, that's not how we scroll the chat log. So if we go back to here, and then I put this on the screen. Boop. I gotta actually click the thing first. Hold on. That's not really centered at all. Good job, me. There we go. That's good enough. If you go to this, you can actually play with the geometry of any of these things that we made. So let's suppose that I have 6 things around the central atom, and you want to know its electron pair geometry. That's listed right here. And then over here, the molecular geometry will also be shown. And that changes if you add in extra things. You can even turn on the bond angles too if you'd like. And then the next thing you can do is you can get rid of the lone pairs so that we treat them as invisible. So here's what my square pyramidal would look like. You can see the square bottom, like this, and then there's just one coming out of the top. If I get rid of that one, and I add in a... Oh, I have to actually turn these on to do that. And then I remove the lone pairs. There we go. So that's what square planar would look like. So you can play around with the molecular geometry simulator, and you can even test yourself. You just turn these off and be like, okay, I'm going to just go pew, 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 pew. What is this called? You're like, oh, it's T-shaped. Hooray. There you go. So you can test yourselves with this. The only thing is that the textbook, for some reason, calls them molecular shape. Everyone else in the world calls it molecular geometry, so that's what this means right here. Electron geometry and electron pair geometry are close enough that you should be able to identify those. Okay, so that's how we do shapes. Any questions, let me know. So let's start assigning shapes to stuff. So how do we do this? First, you got to draw a Lewis structure. Second, you got to determine which category it goes into for electron pair geometry. So it's either going to be linear, trigonal planar, tetrahedral, trigonal bipyramidal, or octahedral. And then you start deleting domains for the non-bonding pairs and choose which member of the family it ends up being. So if I were to go back to, say, my chart here, and I had a molecule that had 5 electron domains, of which 2 were non-bonding pairs, I would find 5 right here, and then I would go to 2, and that's the name of the shape. All right, so let's do some examples here. So ammonia is really simple. Draw the structure for ammonia real quick. I'll give you a minute to do it. And what I want you to do is assign an electron pair geometry and then a molecular structure for ammonia. I think the hardest part of using this table is actually remembering the terms. Electron pair geometry is just the category, and molecular structure is the specific member of that category. So go ahead and do that. We'll go over the answer in just a second. All right, hopefully you drew something that... Oops, that's not the pen. There we go. Hopefully you drew ammonia like this. Because then we got to correct it for geometry. So what we're going to do is we're going to count electron domains. That would be how many places are electrons around my atom in the center. So there are 4 electron groups. And I want to call it Vesper. I want to call it electron geometry. So the electron geometry is tetrahedral. And of those 4 electron groups, one of them is an electron pair, which means that its molecular shape is trigonal pyramidal. And then if I was going to draw the shape more accurately, I would grab the template that looks like a tetrahedron and I would draw it like this. That's what ammonia actually looks like. And it looks like you guys have the idea. So let's go straight to the examples here. This is just talking about how we want to take from the equatorial positions instead of axial, which we already went over. But here you go. So here's the examples. Oops, I didn't mean to do that. What I want you to do is draw the Lewis structure. You don't have to draw any resonance structures. Just draw one Lewis structure for each of these. And I want you to tell me the electron pair geometry and then the molecular shape for all of them. All right. So go ahead and do that. I'll go over the answers in about 5 minutes or so. How are we doing? Any questions? Let me know in the chat. Just a few more minutes, so we'll go over the answers. Oh, I gotta put that back on the screen here. There we go. So let's look at some of these structures. Oh man, that lovely chart that we just spent all of this time making, yeah, it's gone. Oh, it didn't. I didn't actually delete it. I'm on the wrong layer, that's why. Hold on. Huh. Last time I had to do this, and it's gone. Every year when I draw this chart, I always think to myself, man, it's such a nice chart. I wish I could just keep it forever. And then I erase it. All right. By now, we should be pretty proficient at drawing Lewis structures, so I'm just going to draw the answers because I've more or less memorized these. Because I just want to get to the interesting part, which is the geometry. So I'm going to circle the electron domains around this. There are 3 electron domains. So the electron pair geometry is going to be trigonal planar. And of those 3, one of them is an electron pair. So the molecular shape will be bent. All right, what's the next one? SNCl3. Really, the trick is going to be, can you draw the Lewis structure clearly enough that you don't confuse yourself? And in the next section that we're going to do when we talk about polarity after the break here, that's going to be really important that we draw our shapes very well. All right, so I got SNCl3 here. There's a minus on this. I should do that. So there are 4 electron groups. 1, 2, 3, 4. So the electron geometry is going to be tetrahedral. Of those 4, 1 is an electron pair, so the molecular shape will be trigonal pyramidal. All right, let's go to the next one, SECl2. All right, we'll count electron domains around the central atom. 1, 2, 3, 4. For 4, that's still tetrahedral. Of those 2, or of those 4, 2 of them are electron pairs. So the shape is bent. I I didn't mean to scroll that far down there. There we go. We got carbonate. That looks like this. I didn't put the brackets around it. That's okay. All right. Let's count the electron groups. Remember, double bonds and single bonds still count as one group each. Doesn't matter how many bonds there are. The electrons are in the same spot. So this has 3 electron groups. So the electron geometry is going to be trigonal planar. And the molecular shape, none of them are electron pairs. They're all just bonds. So the molecular shape is the same, trigonal planar. All right. I3 is like one of my favorite molecules ever. Because you draw its Lewis structure, and you go, okay, dot, 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 dot. Wait, I still have 6 electrons left. Got to put them on the central atom. And so you get this crazy nonsense. Can't be tetrahedral bent because bent is not... Well, sorry, tetrahedral is not for the number of electron groups for this, which is there's 2 bonds, but then there's 3 of these guys, so that's 5. So 5 isn't tetrahedral. 5 is trigonal bipyramidal. And then, of those 5, 3 of them are electron pairs. So the molecular shape is linear. Triiodide is linear, which is very bizarre to me. But I also think is really neat. I sat there just pausing, trying to figure out how you got tetrahedral bent out of crazy nonsense, and I was like, huh? Alright, I want to say that this one... Well, I should count these, hold on. 42, 8, 16, 24, 32, 40. Yeah, okay, so this... Suddenly I'm drawing electrons on them, so I gotta do that anyway, so... Have all these electrons. This is the electron sum. I don't know. Alright, there's my structure. 1, 2, 3, 4, 5, 6. 6 is octahedral. Of those 6, 1 is an electron pair. So my shape is square pyramidal. Alright, there you go. That's shapes. Your task is to draw the Lewis structure of any shape. Tell me its electron pair geometry. And then tell me its molecular shape. And then after that, you're going to tell me if it's polar and nonpolar and what direction. But we haven't done polarity yet. That's going to be for after the break. So let's put the... Oh, I'm all over the place. Hold on. Where's my timer? Oh, I really should just update this so that stops popping up. All right, start the clock. We'll see you in a bit to go over polarity. I mean, I was typing about 1 second before that, so I'll take it. Where did my... There it is. Okay, so I gotta go like this. Boop, boop. Okay, so I just had emailed another instructor really quickly about a question that I had about some of the stuff that we cover in this class, and it's like, do we really need to do this thing? And this is Valerie. So I talked to Valerie. She teaches 162 a lot at the college. Like, almost all the 162 is her or Mark. And she says, well, I go over chapter 10 stuff pretty much from the beginning. So you don't really need to do that in 161. And if you're taking Chem 162 in the summer with her, she'll be going over it again on her own then anyway. So what we're going to do is, first of all, I'm going to skip this really quickly. We're going to actually do this section. This is the important one. I'm going to show you the schedule here. So you can see that at the end we have intermolecular forces. We're not going to do this. So it's not going to be on the test. It's not going to be on the final. I do have to go edit the quiz because I did put it in there with that expectation. But that means that the rest of chapter 4 we'll be able to finish today. So let's go back to what I was talking about. Yeah, I was just reading about the PS5 stuff, and I only own like 3 games on my PS4, and 2 of them are Persona 5. So it's like, the other is Final Fantasy 7R. Like, I don't really follow PS5 news that much. So I have no idea if what's going on is good or weird or what. All right. Let's talk really quickly about deviations from Vesper geometry. If you have electron pairs push other bonds away more than bonded electrons do. And so this is where I get the felt tip pen out here. So the bond angles will contract slightly for 1 electron pair, and they will contract more for 2 electrons. You do not need to know these hard and fast numbers. What you will be asked will be things like less than 109.5 or much less than 109.5 due to the amount of contraction. Also, if you have multiple bonds, the same thing happens. So these double bonds will push the electrons in the single bonds just slightly further away. So this angle right here will be slightly smaller. And I think I actually put the numbers in there, yeah. Oh, I'm going to sneeze. Hold on. Oh, I just barely hit mute in time. How does it change our schedule? It probably doesn't. It probably just means that we will finish all the content now. Chapter 10 was really just section 10.1. It's just a little thing that's added in there. I think that was just a decision that was made by the department earlier, and yeah. It's a little out of the way for this chapter anyway. Whenever I ask you to indicate bond angles on something, what I'm going to ask you to do is use the basic numbers that... Where's my cursor here? Oh, I don't have a cursor. Wait, hold on just a second. What? What just happened? Hold on. That's an issue. Hold on. I didn't even click that. Sorry, hold on. What? Sorry, something is going very wonky with my tablet. It's like it totally just became uncalibrated. Oh, this is no good. Okay, well, I'm going to do the best that I can. for each of these molecules right here, or actually, sorry, so for this molecule right here, yeah, my pen isn't working. So like, it's just, it's like it decalibrated or something. Which is, of course, just what I need on the very last part of chapter 4 here. For each of these molecules, I keep saying the wrong word now that I'm all flustered. Okay. Each of these atoms could be treated as a central atom for this molecule, and you can determine the molecular shape of these types of molecules, provided that they have electrons drawn in there. So let me just put the electrons in here. Now I'm doing this with the mouse. So since there are 4 electron groups and 3 of them are bonds and 1 is an electron pair around here, number 1 would be trigonal pyramidal. This would be 3 electron groups, none of which are electron pairs. That would be trigonal planar. This is tetrahedral, and this is bent. Yeah, that's not good. Okay. I'm not sure why that's happening. Sorry, I just keep trying to use the pen and it's not working. I'm going to leave these examples for you. I really do want to talk about polarity, though, because that's kind of the whole last bit of the chapter that I want to get to. So I'm going to leave these examples for you. Down at the bottom, that question is just asking you, hey, now that you know about geometry and you know what bond angle should be, is my picture misleading you in some way? And you should be able to determine pretty quickly, like, which part of that picture is wrong. All right. Back in the start of chapter 3, a thing that we did was we determined the polarity of bonds by looking at their electronegativity of the atoms that were involved in it, and then we drew a polarity arrow. What we're going to do now is we're going to try and do this for all bonds in a structure. And thankfully, I have animated this because I don't have a pen that works now right now. So let's look at this. Let's look at a few examples of this. Okay, so the first thing we're going to do to figure out whether a molecule is polar or nonpolar, we need to identify its Lewis structure and draw the geometry as close to accurate as possible. Then what we're going to do is we're going to draw polarity arrows for each bond. And we're going to draw those along the bonds. So they don't have to be exactly on top of the bonds, but they have to be parallel to them. And then finally, what we're going to do is we're going to add all of those arrows together using vector notation. If you've taken a physics class, physicists love vectors, and vectors add head to tail. What we're going to do is we're going to just sort of show that graphically. And then we are going to say, okay, this is how our electrons are moving. They're being pulled in this direction through our molecule. If electrons get pulled over towards one end of the molecule, then the molecule becomes polar. But if the electrons are pulled in all directions equally and they just more or less stay where they started, the molecule will be nonpolar. And this will make more sense when you see a few examples here. For instance, let's look at carbon dioxide. CO2 has 2 bonds in it. One is pointed towards the left here, the C double bond O to the left. The other is pointed to the right, C double bond O to the right. O is more electronegative than carbon. Carbon is 2.1. Sorry, carbon is 2.4. Oxygen is 3.5, so that's quite a big difference. These are definitely polar bonds. But if I move the electrons in one direction, they get tugged by the other oxygen behind it. And the overall effect is this. If I were to add these 2 arrows together, I would have to do something like this. So here's my first arrow. And I'm going to note that I started right here. I would love to talk about O3, actually, but I don't have a pen to draw it. So we'll get to that in just a second. I'm going to start my first arrow here, and this is where it ended. So the left bond pulls electron density to the left, but the right bond pulls it right back. And you'll notice that we started and ended in the same spot. So the sum of my polarity is 0. And this molecule must be nonpolar because there's no net distribution of electrons. They didn't get shoved over in one direction and stay there. So that's CO2, and you can see that, oh, obviously they're pulled in opposite directions, so the polarity will cancel out. For things that are rotationally symmetric, like SO3, the same thing happens. So here's SO3. I'm going to start down there. And the bonds sort of just pull it all around. Since they're being pulled equally in all directions, the end result is that this isn't polar. But with water, you're going to see really quickly that these don't cancel. I ended somewhere very different than where I started. So water has a net polarity, and the direction of the polarity is the direction that the electrons got moved to. The negative side of the arrow would be the end point, where the electrons are, and the positive side would be the butt of the arrow, or the tail of the arrow. So we would say that water is polar, and SO3 is nonpolar, by drawing these sort of polarity arrows and moving them around. Now, this is actually not very easy to do on paper. And the reason for that is you're not going to draw all your lines the same length. I actually sat here when I was making these slides, and I was able to measure out the lengths of the line so that they were very close to being the same length, which is why they more or less work out. I think I have 4-dimensional ones here. Yeah, so this is almost impossible to do on paper. And you can see that when I try and do this on the computer, like even now, it looks pretty sketchy. But it still almost works. If you try and do this on paper, it's very difficult because it's really hard to draw in 3D. I have a program that just plops out the molecule shape, so I was able to follow that template pretty easily. But if you drew your Lewis structure wrong, so for example, and here I go with the mouse, if you drew your Lewis structure, oh, that's embarrassing. If you drew your Lewis structure like this, oh, please don't laugh at me that I'm using the mouse. That C just looks like it's having a bad day. If you drew it like this, all of your bonds would be at 90-degree angles, and you might think, oh, okay, nonpolar. But then you might get into a situation where you, like, have to erase one of these or something for, like, ammonia. I'm definitely erasing that C. So something like that, you would have the wrong orientation of the polarity, for example. So you figure out the polarity of each bond by looking at the electronegativity table. That's correct. And then you draw those arrows where you point at the more electronegative atom. Now, looking at ammonia here, it's very easy to see. How do we know which direction? The direction is we point the arrow at the more negative side, yeah. Because we had this sort of notation before. I can draw this with my mouse. Remember this? Where I had the negative side was where we pointed it, and the positive side was where the end of the arrow was. I just didn't draw those lines on there, because that would have meant I would have had to have animated like 3 extra things. For ammonia as drawn correctly, you can see here that this is obviously not going to cancel out, because I'm going to just end up way up at the top. But if I were to draw ammonia wrong, such as, say, like this... God, I hate drawing with the mouse. How do people do this? Something like that, where it looks triangular, and then they say, oh, it's nonpolar, where in reality, it is polar because those bonds are actually pointing at the screen to you. And so the polarity would be out of the screen. Okay, so it's very possible for you to mislead yourself when doing these structures, and the only way to make sure that you get the correct polarity is to draw the Lewis structure as accurately as you can by using the templates that we showed you for geometry. All right. And so that's our summary. Draw the Lewis structure as best you can. Draw all the arrows where you point the negative, the most electronegative atom you point the arrow at along each bond. Then follow the arrows. Do the electrons get pulled back to the start, or are they pulled somewhere else? If they're pulled back to the start, that means they're being tugged in all directions equally, and the molecule's nonpolar. If the electrons are pulled away from where they started, then they're being shifted across the entire molecule in that direction. And that means the molecule is polar. Now, what does polarity do? Polarity is interesting to us because polarity means that there is an uneven distribution of charge. And that means that there is a negative end to a molecule and a positive end to the molecule. And if we were doing the intermolecular forces section, I would show you how those things line up. And if I had I could draw with a pen, I would do that. But I'm actually using the pen on the screen right now. Nothing is happening. So I'm just going to reboot my computer after this. But yeah, polarity is actually a really important property. It allows things like solubility. So water, for example, is polar. Water will mix with other polar things because the negative part of water will attract to the positive part of the other thing. But if you mix something like water and hexane, hexane is nonpolar. It's all C's and H's. So water looks at hexane as like, I don't have anything to interact with you with. I'm going to interact with another molecule, water. And so water will all stick together, kind of like it was made of a bunch of little magnets, whereas hexane would just get excluded because it doesn't have any sort of dipole. It doesn't have an interaction. So I have a bunch of Lewis structures for you to draw. What I want you to do is I want you to draw these shapes and then predict the geometry. Is that the last slide? That is the last slide. Unfortunately, I can't even go over the answers because I don't have a pen, and I feel like the only solution that I have is to reboot the computer. But if I do that, the stream will go down. So what I will do is I'll let you try these problems. I'm going to reboot. And if the stream comes back up, it's because it's working and my pen is working. If the stream doesn't come back up, I will just post an announcement that says, hey, the lecture is over. Here are the answers. And then I will draw them on I have a pad of paper here. I could just take a picture of it and then send it up to you. So yeah, you will get the answers to these somehow. But what I'm going to do is I'm going to leave this on the screen. You might want to hit pause on the video because I'm going to hit stop streaming in about 20 seconds here. I'm going to reboot. I'm going to see if that fixes it. And then I'll be back online. So hopefully I will see you in just a bit. All right, the stream's going to stop now.